Welcome to the 32nd lecture of this course. Today we are going to talk about another very important topic in theory of computation, namely that of undecidability. Okay. So, the question that we are going to address today and in the next couple of lectures is, are there problems that cannot be computed using a Turing machine? We will show that there are problems that cannot be computed using a Turing machine. So, they are called undecidable problems, and we will show how to show that certain problems are undecidable and so on. But before I go into the topic of undecidability, let me mention a hypothesis that was laid down by Alonzo Church and Alan Turing. So, it is called the Church-Turing thesis. Okay. So, essentially what they said is that anything that can be computed by a Turing machine. Okay. So, in other words, what this hypothesis says is that Turing machines are a universal, Turing machines can be thought of as a universal model of computation. So, any problem, any computational problem which can be computed by any computational device, for that problem there also exists a Turing machine that can decide that problem, okay, if we represent it suitably in a language format. Okay. So, basically therefore, then in the context of undecidability, what this means is that suppose if I show that a problem is undecidable, in other words if I show that a problem cannot be decided by a Turing machine, it essentially means that it cannot be computed by any computing model or any computing device that is available at hand, okay, if we believe the Church-Turing thesis. Okay. So, this is actually to show that some problems are undecidable is quite a big question, I would say, because if you imagine, I mean with so much computing power that is available to us today, to say that there are languages which cannot be computed is something that is not immediately obvious. Okay. So, before I show the first undecidable problem, let me talk about equivalence of Turing machines and so representing Turing machines by integers. Okay. So, so, in our last lecture I said that any Turing machine, or for that matter DFA PDA, you can represent it using a finite string. Okay. So, a Turing machine also can be represented using a finite string consisting of symbols from some finite alphabet. Okay. For example, if I just represent the description of a Turing machine, that is the transition function, the states, accept state, reject state, it is basically a finite string over some finite sequence of alphabet. Okay. Now, I can convert this this to a binary string. Okay. So, what I mean by this is that I can take the string which represents a Turing machine and I can convert it into a string over 0 ones. The way to do that is, suppose I have a string over an alphabet which has size k. Okay, so, there are k symbols in the alphabet, k can be any constant. So, therefore, to represent I use log k bits, okay, I use log k bits over 0 1 to represent each symbol of the finite alphabet. Okay. For example, if there are 10 symbols in that alphabet, I will use log 10, I will use the ceiling of log 10, which is basically 4. Okay. So, I will use 4 symbols. So, each symbol of the alphabet will be represented by a binary string of length 4. Okay. Now, therefore, I take a string over the first alphabet and convert it into a string over 0 and 1 by replacing every symbol with its corresponding binary string. Okay. Now, to every binary string, we can associate a unique number. Okay. So, every binary string, so suppose if the string does not begin with a 0, then of course, every binary string can be converted into its corresponding decimal string, and that is a natural number. Okay. But suppose if I have preceding zeros, okay. So, for example, if I have a string let us say 0 0 1, okay, and another string 0 0 0 1. Okay. So, both these strings when converted to decimal corresponds to the number or let us take a little bit more. So, let us say I have a string 0 0 1 0 and I have another string 0 0 0 1 0. So, when I convert both these strings into a decimal, it corresponds to the number 2. Okay. So, to avoid this kind of a situation where two binary strings can map to the same natural number, what I do is that I add a 1 at the beginning. So, now if I for example add a 1 to the beginning of every string, so I add a 1 here and I add a 1 here. So, this string now corresponds to some number for, so in this case it corresponds to the number 18, okay, and I think so. So, this will correspond to 18 and this will correspond to 34. Okay. So, they correspond to two different natural numbers. Okay. So, basically if I add as 1 to the beginning of every binary string, then every binary string corresponds to a unique natural number. Okay. Now, to every natural number, we can associate a Turing machine. Okay. So, by this mapping, okay, here for every Turing machine I have a binary string which gives us a natural number. So, there are certain natural numbers which correspond to a Turing machine, but there might also be some natural numbers which do not correspond to a fixed Turing machine. So, what I do in that case is that, so if a number does not map to a Turing machine, by the earlier representation, then we map it. So, then we map it to some arbitrary but fixed Turing machine. Let us say a Turing machine that accepts all its input. Map it to the Turing machine that accepts all inputs. Okay. Basically, what is necessary is to have a function of the following form. So, suppose if I look at the set of all natural numbers, okay, so this is the set of all natural numbers on the left hand side, and on the right hand side, let us say I have the set of all possible Turing machines. So, then I should have a function, okay, let us call it f, from the set of all natural numbers to the set of all Turing machines, such that this f is a onto function. Okay. So, in other words, every Turing machine must have a unique, well, it need not have a unique, but every Turing machine must have some pre-image. Okay. So, therefore, so every natural number gets mapped to a unique Turing machine, and there is no Turing machine that is left out. There is no Turing machine that does not have a natural number as its pre-image. Okay. So, for example, I can map this to a number here, a Turing machine there, and I can map another number to the same machine. I can have a mapping here, something here, and so on. Okay. What is important is that this is a onto map. So, therefore, because I have an onto map, what I can do is that for the jth natural number, okay, we give the following notation. So, let mj denote the jth Turing machine. Okay. So, because for every Turing machine I have a number associated with it. Okay. So, therefore, I can basically number all the Turing machines. Maybe that some of those Turing machines get repeated in the enumeration. Maybe Turing machine number 1 and Turing machine number 5 are the same Turing machine, that is okay. But the point is that for every j there is a Turing machine mj. Okay. So, this is very important, and so this is number 1, and number 2 is I can obviously enumerate binary strings. Okay. So, let Sj be the jth binary string. Okay. So, once again I can look at every binary string. I add a 1 to the beginning of it just to avoid preceding zeros, and then I can just enumerate them. Okay. So, let us say that S0, S1 would be the string 0 or maybe the string epsilon, S1 will be the string 0, S2 will be the string 1, okay. Then S3 will be the string 0 1, and then 1 0, and then 1 1, and so on. Okay. So, I can basically enumerate all strings. So, now that we have these two things, so we have an enumeration of Turing machines and we have an enumeration of binary strings. So, now we are in a position to talk about our first undecidable language. In fact, we will prove something more here. We will give a language that is actually not Turing recognizable. So, a non Turing recognizable language. Okay. So, let us define this. So, I define the language L D as the set of all binary strings S j, okay, such that S j does not belong to the language of M j. Okay. So, this argument is what is famously known as the diagonalization argument. Okay. So, this has been so this was first introduced by George Cantor, and later on it has been used by several mathematicians to prove various results. And this is the result, I mean this is the approach that Alan Turing took, okay, in his famous paper, where he showed that there are problems that cannot be computed by a Turing machine, a diagonalization approach. Okay. So, to understand this language, let me draw a table. Okay. So, we have this semi-infinite matrix. So, it is finite on the left and the top side, and on the right and the bottom it is infinite. So, on the left, on the rows I will put Turing machines. So, first I will have M1, M2, M3 and so on, and on the columns I will have the strings S1, S2, S3 and so on. And the way I fill it up, I fill up this matrix using 0 and 1. So, I say that, so let us give this matrix a name. So, I will call this matrix, let us say L. So, let us give, no, maybe not L. So, I will call this matrix O. Okay. So, O of ij is equal to 1 if Mi accepts Sj, otherwise it is equal to 0. Okay. So, essentially I look at this matrix. So, I look at the first matrix M of the first Turing machine M1. I check whether M1 accepts S1. If yes, I put a 1, otherwise I put a 0, then I go to S2, S3 and so on. So, I fill this up, then I fill the second row and so on. So, the way this language LD is constructed is basically, okay. So, suppose if I have a 1 over here, so let us say I have the following entries 1, 0, 0 and then I have maybe 0, 1, 0 and then 0, 1, 0 in this matrix. What I will do is that I will replace, so I will basically swap the entries of the diagonal. Okay. So, I look at the diagonal of this matrix. If there is a 1, okay, I flip it with 0, and if there is a 0, I flip it with 1. Okay. So, in other words, if I have a 1 in the diagonal, it means that M1 accepts S1, in which case I will not add S1. Okay. So, I will only add those elements of the diagonal which have a 0. So, in this case what we have is that M3 does not accept S3. Okay. So, basically S3 is not, does not belong to the language of M3, in which case we add S3. So, this is what we do. So, we go through the diagonal, whenever we have a 0, I look at the corresponding string, and I add it onto the language LD. Okay. So, add strings Sj such that O Jj is a 0. Okay. So, now that we have this, we can argue the following. So, suppose if Mj okay. So, suppose LD is Turing recognizable. Okay. So, for the sake of contradiction, let us say that LD is Turing recognizable. Okay. So, then there exists a Turing machine, let us call it M, and because I have enumerated all the Turing machine, this Turing machine must be the ith Turing machine for some I. Okay. So, there exists a Turing machine Mi such that LD is equal to the language of Mi. Okay. So, if this is Turing recognizable, it must be accepted by some Turing machine. That Turing machine is somewhere in the row, let us say it is our ith row. So, I say that Mi is the Turing machine. Okay. So, now consider the following case. So, if Mi accepts, so what does Mi do to the string Si? Okay. So, if Mi accepts Si, what do we have? Okay. So, by the, if I look at the definition, so if Mi accepts the string Si, okay, it means I have a 1 on the table, okay, at that point, which means that by the definition of the Turing machine, it should not belong to the language. Okay. So, this implies that Si does not belong to the language LD, because it only accepts those where the corresponding machine does not accept the string. This implies that, so now what is the machine Mi? So, Mi is a machine for the language LD. So, if Si does not belong to LD, then Si also does not belong to the language of Mi, which implies that Mi does not accept Si. Okay. So, we have that if Mi accepts Si, it implies that Mi does not accept Si. Similarly, if Mi does not accept Si, again if I go to the table, I have a 0 over there. So, I flip it to get a 1. Okay. So, if Mi does not accept Si, by the definition Si belongs to the language LD, which means that Si is accepted by the machine Mi. Okay. So, so therefore, we have a contradiction that if Mi accepts Si, if and only if Mi does not accept Si. Okay. So, this gives us a contradiction. Okay. So, therefore, LD is not Turing recognizable. Okay. So, therefore, we have exhibited a language which is not Turing recognizable. Okay. So, next we are going to look at an undecidable problem. Okay. So, so, in our next lecture, we will prove that this language is undecidable. So, the language that we are going to consider is, we define it as follows. So, it is called ATM, and it consists of encodings of a machine M and a string W, such that M accepts W. Okay. So, this is a language which has an encoding of a Turing machine M and a string W. Okay. So, they are given to it together, and it consists of all those pairs such that the machine M accepts W. Okay. If M does not accept W, it is not in the language ATM. Okay. So, in our next lecture, we will prove that this is undecidable, but what we are going to show today is that this language ATM is actually Turing recognizable. Okay. So, we will show that ATM is Turing recognizable. Okay. So, what would be an algorithm to show? So, remember that if I want to show that something is Turing recognizable, then it is enough to show that for instances that are in the language, I have a Turing machine which accepts it, and instances that are outside the language, we do not care. Okay. So, here is an algorithm. Okay. So, given as input machine M and a string W, what the algorithm does, or what the Turing machine does, is it simulates M on W if M accepts W, then accept, and if M rejects W, then just reject. Okay. So, it is a very simple algorithm. So, observe that when I simulate M on W, there are three possibilities. Either M can accept W, or it can reject W, or it can loop forever on W. So, if M accepts W, then it accepts M comma W. Okay. So, it is according to, it is an instance which is in the language ATM. If M does not accept W, if M rejects W, then anyway I am rejecting. Okay. So, it is not here, and if M loops forever on W, then anyway the first step never stops. Okay. So, the first step goes on forever, in which case also I do not accept. Okay. Hence, it is not in the language ATM as required. Okay. So, what we will show in the next lecture is that ATM is not only it is certainly it is Turing recognizable fine, but it is not decidable. Okay. So, I will stop here today. Thank you.